everybody, welcome back to the next video for Unit 3. So we're going to start off today by talking about isotopes. And isotopes are a very big part of elements and the periodic table. And what an isotope is it's elements that are the same, so atoms of the same element that have different mass numbers, or they have a different number of neutrons in the nucleus. So atoms don't have to have a specific number of neutrons. They all, depending on the element, have to have the same atomic number. For example, all of these right here. If I look at every single one of these three examples, they all have one proton in the nucleus. So here's one proton, and one proton. Based on a periodic table, hopefully you could identify that that corresponds to hydrogen. And you can also see that right over here. So all of these are atoms of hydrogen, but they all have a different number of neutrons. So this first isotope has no neutrons in the nucleus. This isotope, also known as deuterium, has one neutron in the nucleus along with the one proton. And this isotope of hydrogen, also known as tritium, has two protons in the nucleus. So it's the same element, but they have different masses. They have a different number of neutrons in the nucleus. We call those isotopes of one another. And we can count the number of subatomic particles or count the number of protons and neutrons and electrons in atoms. So let's go ahead and do that. Or how do we do that? Of course, the atomic number, like we said, is equal to your number of protons. So hydrogen has an atomic number of 1. That means it has one proton in its nucleus. Zinc has 30, an atomic number of 30. That means it has 30 protons in its nucleus. The next easiest subatomic particle that we can determine is the number of electrons. And for this class in chemistry, we can assume that all atoms have a neutral charge. That means their number of protons don't outweigh the number of electrons, or vice versa. So for us in Chem 1, we assume that all of these elements and atoms are neutral. That means that the number of protons will always equal the number of electrons. That just makes life a little bit easier for us. That's one less thing we have to think about. And lastly, how do I find the number of neutrons a particular atom has? And we could do that by finding out the mass number, which is either going to be given to you, or you can find that because the number of neutrons is given to you. So the mass number is always equal to your number of protons plus your number of neutrons. So the number of protons plus neutrons gives us the mass number for a particular isotope. Let's actually go ahead and do some examples. Determine the number of subatomic particles in each of the following nuclides. Let's do sample problem 2. So determine the number of subatomic particles in each of the following nuclides. So here, notice I'm given this nuclide. And basically what that is, it's a particular isotope of an element. So we always have the element name that's given to us. So in this case, the element name, of course, is hydrogen. And then we also have a number that comes after that. And that number is our mass number. So this is the mass number. And this has to be given to you in order to figure out how many neutrons are in the nucleus. So you either have to be given the mass number or you have to be given the number of neutrons. So I have hydrogen 1, and hydrogen 1 is also known as protium. So we can find the atomic number for hydrogen, and it's just 1 because that's its atomic number on the periodic table. By definition, the atomic number is equal to the number of protons. That's literally the definition of atomic number, is it's the number of protons in the nucleus or the nuclear charge. So our atomic number is also equal to 1. And because we're assuming that all of these isotopes are neutral, my number of protons will also equal my number of electrons. And again, that's because we're dealing with neutral atoms. So because they're neutral, your protons equals your number of electrons. Now, don't memorize this table. You're not always going to have a table set up like this. So I see a lot of students sometimes like, okay, every other one is 1. Not necessarily the case. It depends on what the question is asking. So don't memorize the chart. Mass numbers given. In this case, the mass number is equal to 1. So I'm just going to rewrite that here. And now we can find our number of neutrons. If you remember, your mass number is equal to your number of protons plus your number of neutrons. And we've already established that hydrogen 1 has 1 proton in its nucleus. So if the mass number is 1 and it has 1 proton, we know that the number of neutrons has to be 0. And that's because protons plus neutrons equals mass number. You might also see sometimes a nuclear symbol, and that's just another way of representing the nuclide. So the nuclear symbol is H, because of course that is the symbol for hydrogen. And in the upper left-hand corner, you're going to write the mass number. So I'm just going to highlight this again so you know that that happens to be the mass number. And on the bottom is your atomic number. So this right here is atomic number. Notice it's not a fraction, it's just a 1 over a 1. And this top one is the mass number, this bottom one is the atomic number. Let's try hydrogen 2. So the hydrogen 2 is an isotope of hydrogen 1. It's the same element, but they have different mass numbers. So again, this right here is your mass number. I'll highlight that up there as well. So actually, let's just write that down here. Mass number is equal to 2. It's the same element, so my atomic number must be the same. So my number of protons must be the same. So my number of electrons must also be the same. What's different in this example happens to be your number of neutrons. So if your mass number is protons plus neutrons, and you have 1 proton, you must therefore have 1 neutron in the nucleus, because 1 proton plus 1 neutron gives me a mass number of 2. And then of course my nuclear symbol, still hydrogen, except now my mass number is 2, so 2 is going to go on top. And then my atomic number goes on the bottom. Again, this is just a different way of representing this right here. This should really be in parentheses. Deuterium is another word for hydrogen 2. Try this one right here. So I'm going to just write these down. Hopefully you would get something like this. So again, what's the same with all of those? You have 1 proton in the nucleus. The only thing that differs is the number of neutrons, and therefore the mass number differs. All of these right here, these are all isotopes of one another. They are the same element, but they have different mass numbers. Rocco, get off the table. Get down. I'm going to leave that in there so you know what I'm dealing with. He was trying to get candy. So, these are all isotopes. Same element, different masses. Here's a different one. So carbon 13. Let's look up the atomic number. Carbon's atomic number is 6. By definition, that's how many protons it has. And because it's a neutral atom, that will be equal to the number of electrons. Now, they're not always going to be neutral. In Chem 1, though, we just like to make life easy. We'll consider protons always equals electrons. So this 13 is the mass number again. So I'm just going to take that and write that down there. Mass number is equal to protons plus neutrons. Therefore, how many neutrons must be in the nucleus? 7. 6 plus 7 gives me 13. And then my nuclear symbol looks like that. Again, not a fraction, it's just 13 over 6. Let's try helium-4. So, 2 protons. Because its atomic number is 2, and because it's neutral, 2 electrons in its nucleus. Mass number is 4. Therefore, must have 2 neutrons. 2 plus 2 is 4. Symbol for helium is He. Mass number is 4. Atomic number is 2. What I'm going to do is you try the next two and pause this video, and when you come back, I will have the correct answers up. So there are the answers for the last two. This should be a 209, not a 204. So just check your answers. And it's really all the same thing. There are no exceptions to these rules like sometimes you'll see in chemistry. Mass number always equals protons plus neutrons. Atomic number is your number of protons and number of electrons for this class. Mass number over atomic number. Very, very easy concept. And that's it for that. Let's talk a little bit more about electrons, and we're going to do some more examples with electrons in class. So here, like we said, is a very basic representation of an atom. A little bit inaccurate, but that's okay. We could still get the basic idea across. So here's our nucleus. This happens to be sulfur. This nucleus is packed with protons and neutrons. And around this, we have these energy shells. And in this case, we see that there are 3 shells that surrounds the nucleus. So this one right here, the shell closest to the nucleus, is the first energy level. Of course, the second one would be the second energy level, and then the third is the third. We can calculate how many electrons can be held in each sublevel or in each energy level. And we can do that by using the equation 2n squared. 2n squared. So I'm going to cut out here to the whiteboard again, and I'm going to show you how we can determine how many electrons fit in each shell based on that equation. So let's go ahead and determine how many electrons we can put in each individual energy shell, each shell that surrounds the nucleus. We can calculate that by using the equation 2n squared, where n is equal to the energy level. Energy level. So let's say I have in the first energy level, so n equals 1. So this would be the energy level that's closest to the nucleus. I'm going to plug 1 in for n in my equation. So 2 times 1 squared. So 1 squared is 1 times 2 is 2. That means the first energy shell can hold a maximum of 2 electrons, which you'll see in every single picture, every single picture of every element, I should say, that first shell that surrounds the nucleus can only have 2 electrons in it, and it always will, unless of course it's hydrogen, because it only has 1. Let's see how many are held in the second energy level, so that second ring around the nucleus. I have 2, and in this case, n is equal to 2, so we'll do 2 squared. 2 squared is 4, times another 2 gives me 8. So my second energy level holds a maximum of 8 electrons. And we can keep going with this. I mean, you can really calculate how many electrons are held in the 100th energy level, even more than that. Again, let's just plug it in just to see. So 2 times 3 squared. 3 squared is 9 times 2, 18 electrons. So the third energy level holds a maximum of 18. Let's just try 4, just for fun. So oops, I have 2 times 4 squared. So 4 squared is 16 times another 2 gives me 32. So the fourth energy level holds a maximum of 32 electrons. Not a very bad equation, but like I said, you can determine exactly how many electrons can fit in every hypothetical energy level. Really, all you would need to know is really how to go up to 4, and you don't even have to calculate it. Hopefully you would just remember, okay, 2, 8, 18, 32. And that's just for something like kind of extra that we do. But that's how we determine how many electrons. Very simple concept. And the most important type of electrons that you need to know are your valence electrons. And hopefully you learned a little bit about valence electrons in your element project research. And valence electrons are the number of electrons in the outermost shell. And they're so important because they help to determine how atoms will bond to other atoms. So your alkali metals, for example, all have one valence electron. And that's why they all react so similarly to one another, is because they have the same number of valence electrons. Same thing with the noble gases, and same thing with the halogens, and all of your other groups of elements for that matter. So here's sulfur again. Let's count how many valence electrons sulfur has. So we're going to look at this outermost energy level. So this third one, these are my valence electrons, the one that's farthest away from the nucleus. Sulfur has 1, 2, 3, 4, 5, 6 valence electrons. And again, that's the number of electrons in that outermost energy shell. These other electrons and the ones closest to them in the shells closest to the nucleus, those are our core electrons. Core electrons are important, but they don't really help to determine the chemical behavior of an element. We really mostly care about those valence electrons because they tell us how an element reacts or bonds to other elements. And there's a really easy way to determine how many valence electrons a particular element has, and that's by looking at groups. So all of your elements in group 1, so your alkali metals and hydrogen, all have 1 valence electron. So everything right here has 1 valence electron. Your alkaline earth metals all have 2 valence electrons right here. We skipped the transition metals. You might have seen in your element research, if you did a transition metal, sometimes they have more than 1 number of valence electrons. We don't like to deal with those. We just like to deal with ones that we know how many they have. So we'll skip the transition metals. Boron's group has 3 going down. All these guys have 3 valence electrons. Carbon's group has 4. Nitrogen's group has 5. You guessed it. Guess how many oxygen's group has? 6. Your halogens have 7 valence electrons. And your noble gases have 8, except for helium. Helium does not have 8. Helium can only have a maximum of 2 electrons because it only has 2 protons. So helium is an exception to that rule. It only has 2 valence electrons. Other than that, the rest of my noble gases all have 8. And that's why the noble gases are very stable the way that they are, is because they have a full outer shell. They have a full octet of electrons, we say. And because they have that full octet, they don't want any more. 8 is great. That's what we say. 8 is great. Atoms want a full outer shell. They want 8 valence electrons, except for helium. But that's how many they want to be stable. And that's why your noble gases don't react. That's it for this section. Hopefully that was a little bit shorter than some of the other ones. We'll get into atomic weight in the next section, and I'll see you in the next video. Bye.